Hello, this is Ricky Rude, Professor Emeritus at the University of Michigan, and this talk is entitled A Strategic Approach to Climate Modeling for Environmental Security. It was given originally on December 6, 2023 at the Chemical Sciences Laboratory at the NOAA lab in Boulder, Colorado. I open by thanking David Fahey for the invitation to give this talk. In 2012, Dave asked me to give a talk on climate model validation, a topic that, in a small world, is surprisingly controversial. Afterwards, through an undefinable internet path, I was asked by two philosophers, Klaus Biesbart and Nicole Somm, to contribute an article to a book, Computer Simulation Validation. The fact that this book was compiled by philosophers is significant and suggests the complicated relation between simulation and reality. I've enjoyed a number of conversations with Dave over the years, and during the pandemic he told me about an effort on geoengineering. Almost impulsively I responded that our models are grossly inadequate to be making decisions about geoengineering. I'm sure that I murmured something about the fidelity of the models and the representation of the basic physics was, from first principles, inadequate. I also quickly stated that the models and the modeling strategy represented by the Coupled Model Intercomparison Project, CMIP, were not the way to pursue modeling for geoengineering, adaptation, and a number of other essential problems that our species will be addressing in the coming decades. In 2022, I gave 3 talks that introduced why I thought CMIP was not a good way to address adaptation. I also explored and exposed some of the philosophical foundations of modeling and the applications of models. These talks were initiated by another philosopher, Monica Morrison, who is at the National Center for Atmospheric Research, NCAR. I arrive at this talk with another invitation from Dave Fahey to discuss a controversial and philosophical topic. It is a topic that, in my opinion, is of unprecedented importance. 2 decades ago, Tony Hollingsworth of the European Center for Medium Range Weather Forecasts wrote on environmental security. Our climate and our environment is changing so rapidly that we need environmental information that keeps up with the times. We cannot thrive by continuing to behave and build as in the past. To be clear, I do not mean here the effects that climate change has on national security, nor is this represented by having climate experts on the National Security Council. I think that this is so important that we need a National Environmental Security Council. In today's talk, I will summarize 2 themes from the earlier talks. First, my experience with CMIP and adaptation applications and why we need to add different approaches to our modeling capabilities. Second, some of the philosophical aspects of the use of models in scientific investigation. Then, I will stumble through something new, laying out the elements of a strategic approach that I propose as a framework for organizing the development of needed model capacity. I will end with some concluding remarks and personal editorial comments about organizations and how we address modeling in the U.S. The climate models that participate in the Coupled Model Intercomparison Project are a unique and amazing resource. These models provide a credible representation of our future that is unique in history. There has been no generation, no group of leaders with such knowledge. We do not have to guess why the planet is warming and the weather is changing. We do not have to rely on conjecture for the need to intervene, limit, and manage the warming. There are model simulations from dozens of institutions in the CMIP database, and each model has multiple configurations. Most of the models have ensembles of simulations, hence there is an enormous amount of data, and it comes from many different sources. The evaluation process developed by CMIP compares the simulations with observations. It also promotes comparative analysis of the performance of models to reveal behavior and sensitivities. This has provided a portfolio of simulations which are exceptional in both characterization of their performance and the description of their uncertainty. The CMIP models are our primary knowledge base about our future climate, and they are often used in adaptation applications. Sometimes they are used directly, and sometimes they are tailored, notably with techniques of downscaling to fit spatial resolution to more local scales. I have been part of a team at the Great Lakes Integrated Sciences and Assessment Center for more than a decade. The primary mission of this team is to support and advance climate adaptation in the Great Lakes region. For projections of the future, a natural place to look first is the CMIP Model Archive and tailored products derived from CMIP. Two important initial steps are to understand a practitioner's problem and then to evaluate the suitability of the simulation to their problem. As a general rule, each practitioner's problem is different and specific to their locality. Most practitioners are attuned to their local weather and geography. Intuitively, they have a feeling about their past weather and that it is changing. They are often informed by vulnerabilities that have been revealed through weather-related damages. Practitioners want to know, for their place, what has changed, how well is geography represented, are the correct weather features present, and are the numbers generated in the simulations convincingly representing local conditions, means, and extremes. These evaluation criteria bring attention to credibility, a statement of whether the model is scientifically adequate to address the application. That is the model fit for purpose? Note, this is the practitioner's evaluation of the adequacy of the simulations to address their problem. Can they defend it? When we take on this evaluation, we encounter a number of hard facts. First, with so many models, uneven documentation, and multiple methods to represent every ingredient algorithm of a climate model, it is difficult to know what you have. Let's focus on the relatively easy question for credibility for the Great Lakes. Do the models explicitly represent the lakes? This is a question that took us several years to answer and document. After finding the models with the lakes, we then seek to find out, how are the lakes represented? How does the representation influence the performance of the models? All of this comes before perhaps what should have been the first question relative to a city along the coast. Do the models represent lake effect precipitation? The scientist model developer who maintains, perhaps correctly, that the North American Great Lakes are inconsequential to the Earth's climate does not carry the day in Marquette, Michigan. The model is not credible or salient to that application. Addressing application-relevant practitioner questions reveal that simply to answer the first questions of credibility and potential suitability of simulations, the complexity of the CMIP suite of simulation is, in and of itself, a barrier. It points to the need of well-documented models whose design and implementation have the structural elements for a region. In addition to the structural barriers that come from both the complexity of the database and the construction of the models, there are basic performance issues. These are related to the importance of the representation of weather features and large biases in primary variables and derived budgets. Focusing on the quality of the simulations, our evaluations quickly revealed that the models have an inconsistent representation of weather processes. Wintertime precipitation is more convincingly represented than summertime. Important weather features are absent. This presents the practitioner with uncertainty descriptions that are seasonally dependent. More consequential in terms of model performance is bias. The bias in basic model variables is large and it is not random. This is especially notable for precipitation. If we examine the bias in important budgets such as those needed to determine lake levels, which requires precipitation, evaporation, and runoff, then we find that bias errors in the budget terms are as large or larger than the terms themselves. Can we correct the biases? Bias adjustments that are comparable in size to the physical terms are in effect additive terms to the model equations. They have no physical foundation. They are not corrections, they are adjustments. Large biases raise scientific and ethical questions about the representation of geophysical knowledge in the models. Are we ethical in our presentation of our certainty in our knowledge? The evaluation suggests that for this application we are reaching too far. The CMIP models are not fit to this purpose. Tailoring the global simulation through either statistical or dynamical downscaling does not correct these deficiencies in any fundamental sense. The tailoring inherits the errors, it does not fix the errors. Interrogating the CMIP models for adaptation relevant information is productive. However, their direct application of numbers from these models to adaptation problems is difficult to defend. It is an easy extension of reason to maintain that it would be difficult to defend their use in decision-making for problems such as geoengineering. Models are so ubiquitous and integrated into scientific investigation that we often forget we're using models. A figure describing the greenhouse effect or an ideal schematic of atmospheric transport is a model. The ideal gas law is a model. Our understanding of climate is based first on observations, then on mental models, heuristic models, statistical models, parameterizations, approximations, process models, and component models that are constructed into comprehensive models. We are likely to forget that a model is only a description or a schematic of a system, theory, or phenomenon. We come to believe our models as if they are nature, as if they are the things we choose to represent. We keep building more and more comprehensive models that include humanity. These models aspire to represent decision-making, which is even less deterministic than the climate. Some talk about digital twins, claiming that they are the key to, quote, for the first time, easily accessible kilometer-scale climate information to manage the planet sustainably. In the more mundane scientific world, models should be built for purpose and they should be evaluated for purpose. They are tools that we use to probe, analyze, and understand the natural world. They can help us explore. They will, however, never be an equivalent representation of the natural world. This is emphatically true for models that are discrete numerical representations of the approximate continuous and statistical equations that we use to describe and understand our incompletely observed climate. Above, in the case study on Great Lakes adaptation, we were examining whether or not simulations in the CMIP archive and their derivatives were fit for purpose in our adaptation application. We concluded, after several years of work, that they were not. If climate poses urgent problems, then we need to move more quickly to addressing problems rather than determining whether existing simulations are fit for purpose. We need collections of models that are designed for purpose, evaluated for purpose, and documented for purpose. We need models that are available and usable. Let's describe how models are used in weather forecasting. In weather forecasting, we have observations, and we want to project an observed state into the future. We have multiple types of models at different scales. Famously, we have the global medium-range models. We have limited area models. We have different models for storms over land than for over water. We have single column models that are used to analyze individual measurement profiles. We have the models that express the basic theory that connect thermodynamic variables, the relationships between water and temperature. These provide consistency checks and physical plausibility. We have models from different institutions. We have the expertise of forecasters who know a local region. They know the systematic errors of models. They know that different models are providing different information that is ultimately complementary. The information from several models serves as guidance that, in concert with observations, theory, and experience, contributes to a forecast determined by expert interpretation. The model simulations do not provide the forecast. It is critical, as we think of the difficult problems associated with a changing climate, that we are anchored in a philosophy that models are tools to assist and guide our reasoning and conclusions. I stated above that I think that this subject is of unprecedented importance. Why? Though we have the historically unique knowledge that the climate is warming, and we know why, the path forward is quite different from the path that guides us here. We are at a frontier, looking across a climate wilderness that is both familiar and alien. Models offer us guidance for that frontier. We know there are some cliffs and chasms, but we don't know where they are. The models are like maps from scouts and guides, from the explorer. Unfortunately, they are time maps rather than spatial maps. Hence, the peril and possibility are always difficult to know. If we are going to benefit from our knowledge of the future warming climate, we need models that are careful probes of the fuzzy forms that we see on the path ahead. We do not know how to manage non-stationarity. Consider the construction of buildings, bridges, and roads. Historically, the design and specifications have relied on a weather file, perhaps representing a typical meteorological year. What now is a typical meteorological year? Climate Forward, how architects and engineers aren't using climate projections to inform design, is a recent report compiled by the national architectural firm HGA. Presently, the vast majority of buildings being designed do not use environmental conditions that represent the current conditions. There are no accepted standards of data or practice. There is liability for designers and engineers to use data and protocols which are not standardized. Likewise, there is recognition that there is liability for not planning for the climate in the future. We need models designed for monitoring and predicting the stationarity. We need discriminatory methods of describing and managing uncertainty. The challenges of design in civil engineering represent, perhaps, a chronic condition. Here are some more acute conditions. We need to be probing tipping points with methods focused on tipping points. Our methods of managing emissions and balancing air pollution against warming require far better models than we now have. There are projects of regional geoengineering, such as whitening ice sheets and greening deserts, that have massive climate and geopolitical consequences. If we are to make decisions on implementation of solar radiation management, and we will, models will be a primary tool, if not the primary tool. They will inform science-based evidence. The risks and consequences for these decisions are outside of the scope of any decisions yet made by humanity. It would be neither scientific nor ethical to provide knowledge for decision-making for these challenges without having models and complementary elements of investigation designed for a specific purpose. In many cases, it is easy to point out what is deficient in an existing practice. It is difficult to pose something that is better, much less right. To address our needs for environmental modeling, the issues are far larger than simply building models and running them. There are measurements, experiments, campaigns, and complementary research that establish the models as robust scientific tools. There are institutional resources, protocols, and practices that encapsulate such an effort. The entirety of the system will not be outlined here. The focus will be on the modeling. In all cases, it is recognized that we are not talking about just one model or the model. we are discussing a set of models that is used to investigate a specific problem. This will be referred to as the model set. First, the model set needs to be built for purpose of an application. This requires knowing the application and its inquiry well enough to develop an evaluation path that is relevant to the application and that can determine fit for purpose. It requires knowing the application well enough to describe the structural elements of models that describe the essential physics, chemistry, and biology. Simulation suites need to be designed within the evaluation plans. Second, the number of model sets and modeling institution needs to be small and focused. At some size, the logistics of the multi-model ensemble are too slowing for the urgency of the applications. The number of models needs to be decided on a scientific and resource basis. There needs to be a focus on process-based development of a small number of excellent models. Third, the model set needs to exist in a software framework and development environment that supports controlled experimentation. As this is a multi-scale problem, the requirement for interpretation at the interfaces between the scales needs to be designed into the framework and to be as robust as possible. The models need to be well documented and on defined, described, and transparent development paths. Fourth, the model set needs to serve both operations and research. The models need to have an operational predictive part of their mission. The models need to support hands-on configuration, modification, simulation design, and implementation by application experts. I note that nothing in these 4 points is new. We have fragmented capacity that should serve as an excellent foundation. It is a choice of whether we use that or decide to reinvent. I will start with the figure from above when I described weather forecasting. At this point, the figure is used only to establish that the model set provides guidance in a research process that includes measurements, experiments, campaigns, and complementary research. The figure is also used to establish a notional proposal of what comprises a model set. The notional model set includes an ecosystem of models of different scales and purpose. These include global, regional, phenomenological, process, impact, and post-processing and tailoring. One of the most important considerations in development of a strategy is to think about the important spans of time and a notional workflow from a use case. Here I will use adaptation because, for me, it is more well known than notional. If we consider time spans on which we plan, we find many important decisions of public, private, and individual investments are on decadal time spans. If we look at typical projects, they include planning, design and engineering, permitting, implementation, and use. We pose here a 50-year use time. At this point, the climate is changing significantly on a decadal time span, and the evidence suggests this will remain true for all reasonable planning and implementation horizons. We will be in a state of constant monitoring and replanning. Currently, CMIP, analysis, and model use evolved on a half-decadal to decadal time span. The urgency to address these problems and the non-stationarity of climate require us to decouple adaptation, geoengineering, examination of tipping points, and many other problems from CMIP. We need a routine operational capacity producing simulations on decadal time spans. Next, I want to modify the notional model set. I will focus on a couple of items that I think are most deficient. I first alter and expand the global model type. It is essential that we move away from our high reliance on ad hoc ensembles and ensembles of opportunity. The roles of ensembles in prediction are so important that we need to elevate science-based purpose-based design. We do need to maintain CMIP and CMIP-type approaches. The strengths of CMIP-type approaches are too many to enumerate here. The CMIP archive is often the first database of exploration and interrogation. Given the human, monetary, and computational resources required, CMIP-type simulations need to be appropriately sized to the model set as a whole. We need global predictive models with focus on a 10 to 50-year event horizon. This is a time span that has traditionally been not only ignored because of perceived predictive challenges, but dismissed. I assert that at least part of this dismissal is because of the bias in our community to view problems from an atmospheric and weather perspective. Experience shows that if we actually focus on a problem, then we better examine the physics and the processes. Of critical importance is better inclusion of the oceans and interactions of the ocean with the atmosphere. Important aspects of this focus include the monitoring and understanding of the warming, sea level rise, changes in regimes of precipitation and evaporation, ecosystem changes, compound events, adaptation, geoengineering, and effectiveness of mitigation policy. Of primary importance is the reduction of bias in key variables. The atmospheric model needs to focus on process, the attributes of weather, namely the role weather plays in the transport of moisture, heat, and momentum. Attention needs to be paid to teleconnections, for example El Niño, and not only the ability to simulate teleconnections, but their relationship to weather features. The design and implementation of the model should presume its interfaces with other models in the model set. I next expand on the regional model types. Regional models have many advantages, including the ability that meaningful simulations can be run on widely available computational platforms. They provide a way to scale across applications and, more importantly, across expertise, training, and local knowledge. Regional models are unlikely to correct the errors, especially the bias errors of global models. Indeed, they will inherit those errors. Therefore, attention needs to be placed on the interfaces, including the development of standard protocols and training to assure that practitioners understand how global models influence regional models. As with global models, it is essential that we move away from our high reliance on ad hoc ensembles and ensembles of opportunity. The roles of ensembles in prediction are so important that we need to elevate science-based, purpose-based design. We need to integrate weather forecasting techniques into the model set. Climate is often defined as the average of weather. It is also useful to think that our climate depends on the cumulative transport effects of weather systems. Furthermore, weather is the way we feel the consequences of a changing climate. Weather is important to the practitioners and the need for local knowledge. The ability to have a weather forecasting capability in the modeling set offers strategies to investigate transport in case studies and use cases, investigate the interchange of energy, momentum, and moisture at surfaces, attribution, and a strategy to manage bias in adaptation applications. This is important for adaptation as initial and boundary conditions that are modified to represent changed climate backgrounds can be used to investigate how storms that have revealed vulnerabilities are modified. It is a way to provide quantitative local information for planning that cannot be derived from global or even regional climate simulations. Such techniques can better manage the biases of global and regional simulations. Ensembles with hundreds of members can be used to explore, for example, a proxy Hurricane Hugo's effects on Charleston, South Carolina. This is a place where methods based on machine learning might be strong contributors. The other types of models, phenomenological models, impact models, process models, and post-processing and tailoring, offer high flexibility, and efforts should be made to integrate them into the model set. I hope I have presented a cogent and convincing presentation that conveys that we are on a path where we have an unprecedented need for model-based science to help guide us into the rapidly changing climate that we have created. I have tried to frame this as our existing models, most notably those associated with the Coupled Model Intercomparison Project, CMIP, have been uniquely successful in providing us with a credible but fuzzy vision of our climate future. We need to develop new approaches to model design and simulation design to provide us tools to clarify that vision. We are sitting at the edge of a climate wilderness, which is both familiar and alien. Models are what we have to help navigate us through that wilderness. I have demonstrated why CMIP and CMIP-like approaches are not sufficient to provide the guidance we need to manage monitoring, non-stationarity, uncertainty, and provide a credible representation of weather. We need better models to inform decision-making for tipping points, managing emissions, is policy working, geoengineering. The list goes on. I have posed some organizing principles for model sets to better provide needed information. These include the fact that models are built and evaluated for purpose, and the primary role of models is to provide guidance in concert with other knowledge to support expert guidance that informs decision-making. It is both sound scientific and ethical practice to derive decision-relevant knowledge from models suitable for purpose. I realize that nothing I propose here is uniquely new. I am also aware that there is an emergent sense in our community that we need new approaches to modeling. Most of what I have seen, however, is anchored around making what we have done bigger and better. What I present here is more connected, and I pose as more strategic. I have been asked, what do I want people to take away from this talk? I think first, if you're in a position of influence, especially in the U.S. government, what we have been doing regarding modeling and modeling policy is not sufficient, adequate, or fit to the purposes of the decisions that we will need to make. There is need for an authoritative, trusted source of model guidance. We can continue to leverage or reframe our current capabilities, but it takes an excessive amount of time, and the outcomes of the effort are difficult to defend. We can continue to fund and manage models as we have, which is minimally inefficient, arguably ineffective, and I assert will become less competitive with other nations. We need to do something different than continuing to do what we know how to do. This is difficult culture change. If you are a scientist or a practitioner who needs model guidance for your work, then you need to develop strategies and skills to extract what you need from our current model knowledge. The good news is that there is, in general, usable and defensible information available. There are strategies that involve developing scenarios and model-informed plausible storylines to manage uncertainty. What I suggest here that we need to explore are evolving techniques that better link predictive science and weather modeling to climate knowledge. This is a strategy to provide quantitative information for planning, design, and engineering. The lack of model guidance, however, is not the most important missing knowledge in addressing climate change. It is knowing how to apply what we have to our real-world problems. This will always be the case. Thank you for listening.